Good day, everyone. I am Allysa Marie Recto, and I am the reporter for the fundamentals of frequency modulation. Now, for the introduction, a sine wave carrier can be modulated by varying its amplitude, frequency, or phase shift. Now, when we say frequency, it is the number of occurrences of a repeating event per unit of time. When we say phase shift, it is how far the function is shifted horizontally from the usual position. The vertical position is how far the function is shifted vertically from the usual position. Now, now for the basic equation for a carrier wave is carrier wave is equal to peak amplitude sine 2 pi frequency plus or minus phase angle. Impressing an information signal on a carrier by changing its frequency produces FM. Varying the amount of phase shift that a carrier experiences is known as the phase modulation or PM. Varying the phase shift of a carrier also produces FM. FM and PM are collectively referred to as angle modulation. Since FM is generally superior in performance to AM, it is widely used in many areas of communication electronics. Now for the first one, the basic principle of frequency modulation. In FM, the carrier amplitude remains constant and the carrier frequency is changed by the modulating signal. As the amplitude of the information signal varies, the carrier frequency shifts proportionately. As the modulating signal amplitude increases, the carrier frequency increases. If the amplitude of the modulating signal decreases, the carrier frequency decreases. The amount of change in carrier frequency produced by the modulating signal is known as the frequency deviation, or what we know as FT. Maximum frequency deviation occurs at the maximum amplitude of the modulating signal. Now the relationship above mentioned is directly proportional. The reverse relationship can also be implemented. A decreasing modulating signal increases the carrier frequency above its center value, whereas increasing modulating signal decreases the carrier frequency below its center value. Normally, the carrier or the figure shown is a sine wave, but it is shown as a triangular wave. Here to simplify the illustration. With no modulating signal applied, the carrier frequency is a constant amplitude sine wave at its normal resting frequency. In telecommunication, a carrier wave, a carrier signal, or just carrier is a waveform, usually sinusoidal, that is modulated or modified with an information bearing signal for the purpose of conveying information. This carrier wave usually has a much higher frequency than the input signal. Next is the modulating information signal, which is shown in the figure above. It's a low frequency sine wave. As the sine wave goes positive, the frequency of the carrier increases proportionately. The highest frequency occurs at the peak amplitude of the modulating signal. Modulation the process in which the carrier signal is varied according to the information bearing signal, also called the modulating signal. During modulation, some characteristics, it can be amplitude, frequency, or phase shift, is varied in accordance with the original information bearing signal that has to be transmitted. The modulating signal is nothing but the information signal. This modulating signal is primarily two forms such as analog signal and digital signal. Now, the difference between the carrier wave and the modulating information signal, carrier wave is just a plain wave without an information, while the modulating information signal is a signal wherein the information was putted to be disseminated. As the modulating signal increases towards zero, the carrier frequency again increases. This phenomenon is illustrated in the figure. An FM signal, where the carrier sine waves seems to be first compressed and then stretched by the modulating signal. As you can see, the first part of the FM signal, it is slightly stretched, and then by the second part, it is already compressed, and so on. Frequency modulation is the encoding of info in a carrier wave by varying the instantaneous frequency of the wave. When the modulating signal has only two amplitudes, the carrier frequency, instead of having an infinite number of values as it would have with a continuously varying analog signal, has only two values. This phenomenon is illustrated. This kind of modulation is called frequency shift keying, or FSK, is widely used in the transmission of binary data in Bluetooth headsets, wireless speakers, and many forms of industrial wireless. Frequency shift keying, or FSK, is a frequency modulating scheme in which digital information is transmitted through discrete frequency changes of a carrier signal. The technology is used for communication systems such as telemetry, weather balloon radio zones, caller ID, garage door openers, and low frequency radio transmission in the VLF and ELF bands. Now, for the part 2, principles of phase modulation. When the amount of phase shift of a constant frequency carrier is varied in accordance with a modulating signal, the resulting output is a phase modulation, or PM signal. Phase modulation is a modulation pattern for conditioning communication signals for transmission. It encodes a message signal as variation in the instantaneous phase of a carrier wave. Note that it is the dynamic nature of the modulating signal that causes the frequency variation at the output of the phase shifter. FM is produced only as long as the phase shift is varying. It is a triangular wave whose positive and negative peaks have been clipped off at a fixed amplitude. During time 0, the signal is 0, so the carrier is at its center frequency. When the modulating signal goes negative, the phase shift becomes leading. the cause the carrier wave to be effectively speeded up or compressed. The result as if the carrier frequency had been increased. Applying this modulating signal to a frequency modulator produces the FM signal, shown this illustration. Now for the explanation, during the time the waveform is rising, or T1, the frequency increases. During the time the positive amplitude is constant, or T2, the FM output frequency is constant. During the time the amplitude decreases and goes negative, or T3, the frequency decreases. During the constant amplitude negative alternation, or T4, the frequency remains constant at a lower frequency. During T5, the frequency increases. Now, to summarize it, the first part, or the TO, it is constant. Then for the T1, the frequency increases. Now for the T2, the FM output frequency is constant. For the T3, the amplitude decreases and goes negative. For the T4, it is also the same as the T3. Now for the T5, the frequency increases. Next is, now refer to the PM signal. During increases or decreases in amplitude, T1, T3, and T5, a varying frequency is produced. However, during the constant amplitude, positive and negative peaks, no frequency change takes place. As the maximum rate of change of modulating voltage occurs exactly at the zero crossing point. In contrast, note that in an FM wave, the maximum deviation occurs at the peak positive and negative amplitude of the modulating voltage. Thus, although a phase modulator does indeed produce FM, maximum deviation occurs at different points of the modulating signal. Now for the relationship between the modulating signal and the carrier deviation. In FM, the frequency deviation is directly proportional to the amplitude of the modulating signal. The maximum deviation occurs at the peak positive and negative amplitude of the modulating signal. In PM, the frequency deviation is also directly proportional to the amplitude of the modulating signal. The maximum amount of leading or lagging phase shift occurs at the peak amplitude of the modulating signal. Although the higher modulating frequency produces greater rate of change and thus greater frequency deviation, this is offset by the lower amplitude of the modulating signal, which produces less phase shift and thus less frequency. Now, for the figures, frequency deviation as a function of, for the figure 1, modulating signal amplitude. Now for the figure B, modulating signal frequency. Now for the explanation, for the figure A, as the modulating signal amplitude increases, the frequency deviation increases. Now for the figure B, as the modulating signal amplitude increases, the frequency deviation remains the same. Now, converting PM to FM. To make PM compatible with FM, the deviation produced by frequency variation in the modulating signal must be compensated for. This can be done by passing the intelligence signal through a low-pass RC network, as illustrated. This low filter, called a frequency correcting network or predistorter or 1 over F filter, causes the higher modulating frequencies to be attenuated. The predistorter compensates for the excess frequency deviation caused by higher modulating frequencies. The result is an output that is the same as an FM signal. The FM produced by a phase modulator is called indirect FM. Indirect FM is obtained by modulation of the phase of the carrier. The instantaneous phase of the carrier varies with the amplitude of the modulating signal. Crystal-controlled oscillators are used to generate indirect FM, and then the result is passed through a frequency multiplier to convert the signal into wideband FM signal. Although the higher modulating frequency produces greater rate of change and thus a greater frequency deviation, this is offset by the lower amplitude of the modulating signal, which produces less phase shift and less frequency. Using a low-pass filter to roll off the audio modulating signal amplitude with frequency. Now for the illustration. Now for the first one, the microphone, and then going to the audio amplifier, and then roll off audio signal with an increase in frequency, then to the phase modulator with carrier oscillator, then the result is indirect FM. Now for the phase shift keying, PM is also used with binary signals, as shows when the binary modulating signal is 0 volts or binary 0, the PM is simply the carrier frequency. For the figure shown, phase modulation of a carrier by binary data produces PSK. The process of phase modulating a carrier with binary data is called phase shift keying or PSK, or binary phase shift keying or BPSK. The PSK signal has a constant frequency, but the phase of the signal from some reference changes as the binary modulating signal occurs. The important thing to remember is that no frequency variation occurs. The PSK signal has a constant frequency, but the phase of the signal from some reference changes as the binary modulating signal occurs. Now for the part 3, modulation index and sidebands. Modulation index and sidebands. Any modulation process produces sidebands. When a constant frequency, sine waves, modulates a carrier, two side frequencies are produced. The side frequencies are the sum and the difference of the carrier and the modulating frequency. In FM and in PM, as in AM, sum and different sideband frequencies are produced. In addition, a large number of pairs of upper and lower sidebands are generated. As a result, the spectrum of an FM or a PM signal is usually wider than that of an equivalent AM signal. It is also possible to generate a special narrowband FM signal whose bandwidth is only slightly wider than that of an AM signal. It is possible to generate a special narrowband FM signal whose bandwidth is only slightly wider than that of an AM signal. In radio communications, a sideband is a band of frequencies higher than or lower than the carrier frequency that are the results of the modulation process. The sidebands comprise all the spectral components of the modulated signal except the carrier. All forms of modulation produces sidebands. Now, the explanation for the figure is this shows the frequency spectrum of a typical FM signal produced by a modulating a carrier with a single frequency sine wave. Note that the carrier and sideband amplitude shown are just examples. Theoretically, the FM process produces an infinite number of upper and lower sidebands, and therefore in a theoretically infinitely large bandwidth. However, in practice, only those sidebands with the largest amplitudes are significant in carrying the information. Typically, any sideband whose amplitude is less than 1% of the unmodulated carrier is considered insignificant. Thus, FM is readily passed by circuits of or communication media with finite bandwidth. Despite this, the bandwidth of an FM signal is usually much wider than that of an AM signal with the same modulating signal. In addition to this, as the amplitude of the modulating signal varies, the frequency deviation changes. The number of sidebands produced and their amplitude and spacing depends on the frequency deviation and modulating frequency. Keep in mind that an FM signal has a constant amplitude, since an FM signal is a summation of the sideband frequency. The sideband amplitude must vary with the frequency deviation and modulating frequency. If their sum is to produce a constant amplitude but variable frequency FM signal. As the amplitude of modulating signal vary, the frequency deviation changes. The number of sidebands produced and their amplitude and spacing depends on the frequency deviation and modulating frequency. Keep in mind that an FM signal has a constant amplitude, since an FM signal is a summation of the sideband frequencies. The sideband amplitude must vary with frequency deviation and the modulating frequency if their sum is to produce a constant amplitude but variable frequency FM signal. Now for the modulation index. The ratio of the frequency deviation to the modulating frequency is known as the modulating index or MF. Now for the formula. Modulation index is equals to FD over FM, wherein FD is is the frequency deviation and FM is the modulating frequency. Sometimes the lower case Greek letter delta is used instead of FB to represent deviation. Now for the other formula, it can be modulation index is equals to delta over modulating frequency. That means frequency deviation is equals to delta. In most communication systems using FM, maximum limits are put on both the frequency deviation and the modulating frequency. When the maximum allowable frequency deviation and the maximum modulating frequency are used in computing the modulation index, MF is known as the deviation ratio. Now for the deviation ratio, it is the ratio of the maximum permitted frequency deviation or delta max to the maximum permitted modulating frequency or Fi max. Now for the first one, I'll be giving you an example. What is the deviation ratio of TV sound if the maximum deviation is 25 kHz and the maximum modulating frequency is 15 kHz? Now for the solution, using the formula MF is equals to FD or F over FM, or modulating frequency is equals to frequency deviation over modulating frequency. Now, substituting the FD and over FM, we will get 25 over 15 kilohertz. And that will be 1.667. That's the final answer. Now for the Bessel function. Given the modulation index, the number and amplitudes of the significant sidebands can be determined by solving the basic equation of an FM signal. The term whose coefficient is MF is the phase angle of the carrier. Note that this equation expresses the phase angle in terms of the sine wave modulating signal. This equation is solved with a complex mathematical process known as Bessel functions. It is not necessary to show the solution, but the result is as follows. Now, that will be the result of the Bessel function, wherein WC is equals to 2 pi Fc for the carrier frequency, and then Wm is equals to 2 pi Fm or is equals to modulating signal frequency. Now for the Vc is equals to peak value of unmodulated carrier. The amplitudes of the sidebands are determined by the Jn coefficients, which are in turn determined by the value of the modulation index. These amplitude coefficients are computed by using the expression. Now that was the expression, wherein the exclamation point sign is equal to factorial, n is is the sideband number 1, 2, 3, or etc. N is 0 is the carrier. MF is equals to FD over FM, or the frequency deviation. The FM wave is expressed as a composite of sine waves of different frequencies and amplitudes that, when added, give an FM time domain signal. Note that, in practice, you do not have to know or calculate these coefficients, since tables giving them are widely available. The Bessel coefficients for a range modulation index are given in the figure, while the first formulas and the expression that was given to you. You do not have to calculate those coefficients. You can use the Bessel coefficient for a range of modulation indexes which are given in the figure. Plot of Bessel function data. Now that was the plot of Bessel function data. Now for an example, what is the maximum modulating frequency that can be used to achieve a modulation index of 2.2 with a deviation of 7.48 kHz? You can pause this video and solve it by yourself. Now for the solution, using the formula, Fm is equals to Fd over Mf. Fm, or the modulating frequency, is equals to, substitute the given data, 7.48 kHz over 2.2, and that it will be giving you 3,400 Hz, or 3.4 kHz. Example of FM spectra. First is the modulation index of 0. Now this is the figure. Now for the example of FM spectra number 2, modulation index of 1. Now this is the figure. Those ranges with 1 below, and you can see any point that ranges from 1 exceeding 1. Now, example of FM spectra, modulation index of 2. Now for an example of FM spectra, modulation index of 2.25, or NBFM, or narrowband FM. Now you can see at the left side of the figure, FC minus FM. Then for the right side, FC plus FM. The primary purpose of NBFM is to conserve spectrum space, and MBFM is widely used in radio communication. Now for the FM signal bandwidth. As stated previously, the higher modulation index In FM, the greater the number of significant sidebands and the wider the bandwidth of the signal. When spectrum conservation is necessary, the bandwidth of an FM signal can be deliberately restricted by putting an upper limit on the modulation index. The bandwidth can then be determined with a simple formula. Bandwidth is equals to 2FM N, wherein FM is equals to highest modulation frequency and N is the number of significant sidebands. The total bandwidth of an FM signal can be determined by knowing the modulation index. For the continuation, another way to determine the bandwidth of an FM signal is to use the Carson's rule. This rule recognizes only the power in the most significant sideband with amplitudes greater than 2% of the carrier or 0.02 or higher. This rule is bandwidth is equals to 2 FD max plus FM max. As you can see, you can calculate bandwidth using those two formulas. Now for an example, what is the maximum bandwidth of an FM signal with a deviation of 30 kHz and a maximum modulating signal of 5 kHz as determined by letter A, Bessel coefficients for a range of modulation indexes, and B, Carson's rule. You can pause this video and solve it by yourself. Now for the solution, now for the letter A, using MF is equals to FD over FM by substituting the given data, 30 kHz over 5 kHz, it will be giving you 6. Bessel coefficient shows 9 significant sidebands spaced 5 kHz apart for MF is equals to 6. Using bandwidth is equals to 2FMN, bandwidth is equals to 2 times 5 kHz times 9, and it will be giving you 90 kHz. 9 can be shown in the Bessel coefficient. Now for the letter B, using bandwidth is equals to 2FD max plus FM max. Bandwidth is equals to, substituting the data, 2 times 30 kHz plus 5 kHz. Bandwidth is equals to 2 times 35 kHz, and it will be giving you 70 kHz. 90 kHz and 70 kHz are the final answers. Now for the noise suppression effects of FF. Noise is interference generated by lightning, motors, automotive ignition systems, and any power line switching that produces transient signals. Such noise is typically narrow spikes of voltage with very high frequency. They add the signal and interfere with it. Now that was the illustration of a signal getting interfered by a noise spike. FM signals, however, have a constant modulated carrier amplitude, and FM receivers contain limiter circuits that deliberately restrict the amplitude of the received signal. This does not affect the information content of the FM signal. Now for the noise and phase shift, the noise amplitude added to an FM signal introduces a small frequency variation or phase shift, which changes or distorts the signal. The carrier signal is represented by a fixed length or amplitude. Phase or S. The noise is usually a short duration pulse containing many frequencies at many amplitudes and phases according to Fourier theory. Now that was the Fourier theory. Now, Fourier theory. Carrier signal is equal to phase shift or rad times frequency of modulating signal. Now, the frequency deviation produced by noise is the symbol. How noise introduces a phase shift. Now, that is the illustration of how noise introduces a phase shift. Now for the preemphasis. Noise can interfere with an FM signal and particularly with the high frequency components of the modulating signal. Since noise is primarily sharp spikes of energy, it contains a lot of harmonics and other high frequencies components. These frequencies can be larger in amplitude than the high frequency content of the modulating signal, causing frequency distortion that can make the signal unintelligible. Most of the content of a modulating signal, particularly voice, is at the low frequencies. In voice communication system, the bandwidth of the signal is limited to about 3 kHz, which permits acceptable legitimately. To overcome this problem, most FM signals use a technique known as preemphasis that helps offset high-frequency noise interference. At the transmitter, the modulating signal is passed through a simple network and that amplifies the high-frequency components more than the low-frequency components. Now, for the difference between the preemphasis and the emphasis. Since the high-frequency components are usually at a very low level, noise can obliterate them. To overcome this problem, most FM signal systems use a technique known as preemphasis that helps offset high-frequency noise interference. To return the frequency response to its normal or flat level, a de-emphasis circuit, a simple low-pass filter with a time constant of 75 nanoS is used at the receiver. The combined effect of preemphasis and de-emphasis is to increase the signal-to-noise ratio for the high-frequency components during the transmission, that they will be stronger and not masked by noise. Now, for the given figures, the preemphasis and the emphasis for the letter A, preemphasis circuit. Wherein Fu is equals to R1 plus R2 over 2 pi R1 R2 C. Now for the letter B, that was the preemphasis curve, which demonstrates the preemphasis circuits. Now for the letter C, that is the de-emphasis circuits, wherein FL is equals to 1 over 2 pi RC. Now for the letter D, the emphasis curve, or the curve that demonstrates the emphasis circuit. Now for the letter E, the combined frequency response, where you can see F is equals to 1 over T is equals to 2.123 kilohertz. The amplitude, pre-emphasis frequency response, the combined frequency response, and the emphasis frequency response. That was the overall effect of pre-emphasis and the emphasis. Now, for the last part, frequency modulation versus amplitude modulation. First was the advantages of FM. Number 1, noise immunity. The main benefit of FM over AM is its superior immunity to noise, made possible by the Clipper limiter circuits in the receiver, which effectively strip off all the noise variation, leaving a constant amplitude FM signal, although clipping does not result in total recovery in all cases. FM can nevertheless tolerate a much higher noise level than AM for a given carrier amplitude. This is also true for phase shape induced distortion. Now, as you can see, as it is stated, FM is more superior to noise than AM. Now for the letter 2, the advantages of FM were the capture effect. Another major benefit of FM is that interfering signals on the same frequency are effectively rejected because of the amplitude limiters and the demodulating methods used by the FM receivers. A phenomenon known as the capture effect takes place when two or more FM signals occur simultaneously on the same frequency if one signal is more than twice the amplitude of the other. The stronger signal captures the channel, totally eliminating the weaker signal. With modern receiver circuitry, a difference in signal amplitudes of only 1 decibel is usually sufficient to produce the capture effect. Although the capture effect prevents the weaker of two FM signals from being heard when two stations are broadcasting signals of approximately the same amplitude. First one may be captured and then the other. This can happen when a driver moving along a highway is listening to a clear broadcast on a particular frequency. At some point, the driver may suddenly hear the other broadcast, completely losing the first, and then just as suddenly hear the original broadcast again. Which one dominates depends on where the car is and on the relative signal strengths of the two signals. Now, for number 3, the advantages of FM is transmitter efficiency. A third advantage of FM over AM involves efficiency. Recall that AM can be produced by both low-level and high-level modulation techniques. The most efficient is high-level modulation, in which a Class C amplifier is used as the final RF power stage and is modulated by a high-power modulation amplifier. The AM transmitter must produce both very high RF and modulating signal power. In addition, at very high power levels, large modulation amplifiers are impractical. The AM signals is generated at a lower level and then amplified with the linear amplifiers to produce the final RF signal. Linear amplifiers are either Class A or Class B and are far less efficient than Class C amplifiers. FM signals have a constant amplitude, and it is therefore not necessary to use linear amplifiers to increase their power level. In fact, FM signals are always generated at a lower level then amplified by a series of Class C amplifiers to increase their power. The result is greater use of available power because of the high level of efficiency of Class C amplifiers. Even more efficient Class D, E, or F amplifiers are also used in FM or PM equipment. Now going to the disadvantage of FM. For the number 1, excessive spectrum use. Perhaps the greatest disadvantage of FM is that it simply uses too much spectrum space. The bandwidth of an FM signal is, in general, considerably wider than that of an AM signal, transmitting similar information. Although it is possible to keep the modulation index low to minimize bandwidth. Reducing the modulation index also reduces the noise immunity of an FM signal. Since FM occupies so much bandwidth, it is typically used in those portions of the spectrum where adequate bandwidth is available. Now for number 2, circuit complexity. One major disadvantage of FM in the past involved the complexity of the circuits used for frequency modulation, with the modulation in comparison with the simple circuits used for amplitude modulation and demodulation. Today, this advantage has almost disappeared because of the use of integrated circuits. Although the ICs used in FM transmission are still complex, they require very little effort to use and their price is just as low as those comparable AM circuits. Since the trend in electronic communication is toward higher and higher frequencies, and because ICs are so cheap and easy to use, FM and PM have become by far the most widely used modulation method in electronic communication today. And that would be all. Thank you and God bless.